In this video, we'll look at verifying trigonometric identities. So if you haven't already looked at the video involving trigonometric identities, I highly suggest you go back and look at that. That is definitely a required set of knowledge for this video. So I think the best way to do this would be to just look at an example. So we look at verifying trigonometric identities as a way of essentially proving that these things are true. Now it's not so much like you're solving a math problem or writing a proof. It's a weird combination of the two. You're manipulating an equation until you get it to something that you know to be true. So let's take a look at this example. I have tangent squared of theta plus 1 is equal to secant squared of theta, and I want to know if this is true or not. So a method, and there are several methods you could use here. The method that seems to generally work for the most cases is your first step. You may notice we have tangent and secant here, and if you consider the last video, we have the ability to turn all trigonometric expressions into something involving sine or cosine, either one or both. So let's go ahead and do that, and then we can see perhaps what's going on here. So tangent, if you remember, that was sine over cosine. So tangent squared of theta would be sine squared of theta over cosine squared of theta. The 1 I'm just going to leave, so plus 1. Secant, if you remember, that's 1 over the cosine. So 1 over cosine squared of theta for secant squared of theta. So if we look at this, I don't have any identity that looks like this with these denominators here. However, I am noticing that both of those are cosine squared of theta. So if I multiply both sides of the equation entirely by cosine squared of theta, those will cancel. Now I have to be careful that I multiply everything, including this 1 here. But the idea is, okay, I can get rid of that and then I don't have these denominators, I just have the numerators. So if I'm looking at this first fraction, the cosines cancel, leaving me just sine squared of theta. Now I have to distribute this thing to both. So 1 times cosine squared of theta will be cosine squared of theta. And then likewise, the cosines both cancel, leaving me just a 1 from up here. Now this is our very first Pythagorean identity that we talked about in the last video. Sine squared plus cosine squared of theta equals 1. At this point I can stop. I have shown, I verified that this works. So when you're going through these, they may not all involve a squared, but you can turn them all into sines, cosines, and then work it down to something that you know or something that obviously has to be true. If you work it down and you get 1 equals 1, you've then verified that the identity does work. This is just one example, but overall the process will still remain the same. Turn everything into sines and cosines, try and simplify as much as you can, get rid of denominators where you can, and try and work it, play with it until you see an identity that you already have. And if you remember, we do have a good number of identities that we've already established. So feel free to check out the video on the trigonometric identities if you're unsure as to what those ones are. There is a final slide where I do have the whole list if you want to check it out. So before we end this video, let's take a look at one more example. I feel like the more you do these, the more it makes sense. It's kind of one of those things. So let's take a look at this example. I want to verify if this identity does indeed hold true. So I have sine squared of theta divided by the quantity of 1 minus cosine of theta is equal to 1 plus the cosine of theta. So looking at this, I don't have any identities where 1 minus cosine is in the denominator. So I think I'm going to multiply both sides by that. So if I do that, that will leave me with sine squared of theta is equal to 1 plus cosine of theta times 1 minus cosine of theta. All I've done is essentially just multiply this expression on both sides. So, next step, if I'm looking at this, I'm looking at this expression on the right, and this looks a lot like a foiling opportunity here. So, if I want to simplify this right side, I'm going to have to FOIL it out, meaning that I will have to take these two terms times each other, and then I will have to do this. Now, you may notice this looks like a difference of two squares. So if we look at this, 1 times 1, well, that's 1, so that one's pretty easy. Cosine squared times a negative cosine squared, or cosine is going to be a negative cosine squared. May have let that one slip. Okay, then I'm going to have cosine times 1, which is just cosine, positive. Then I have cosine, or 1 times a negative cosine, which is going to be a negative cosine of theta. You may notice that these two bottom terms here will cancel out, which will work out for us. So, next step in the equation, I have sine squared of theta is equal to what's left up here, 1 minus cosine squared of theta. And you may look at this and think, that's pretty close to the Pythagorean identity that we already know. And it is. If I add cosine squared of theta to both sides, that will cancel out this one on the right, and I'll have sine squared of theta plus cosine squared of theta is equal to 1. So with a lot of these, sometimes it's not about the substitution. Sometimes it's about just playing with it and doing the algebra and seeing what happens. So at this point, I've hit the Pythagorean identity, which this one does pop up a lot. It's not the only one that you'll see at the end, but if you do get to this at the end, you know this to be true. And we've shown that all of these equations going all the way up are all equivalent, so therefore, this one at the top must be true, because this one on the bottom is true. So then I could say I've verified the identity. All of this work kind of shows that this is true.